Hi everyone. Today I will talk about computing small volume confidence sets for arbitrary distributions. This is based on joint work with Chao Gao from U Chicago, History Universe, and Liren Shan from Northwestern University. So first, we will talk about the prediction problem, which is quite common and popular tasks used widely in real world. For example, they are used in medical diagnosis. We need to predict whether a patient is healthy or sick based on some medical tests, or used in self-driving cars or robot planning. For example, we need to forecast the trajectory of humans or self-driving cars. It is also used in time series forecasting, like in financial markets. One of the most common prediction problem would be the value prediction, or you can think of a regression setting, which is as follows. You are giving a bunch of historical data points, x1, y1 to xn, yn. So x would be the feature and y would be the label for it. And now you have a new input data point with a feature x, and you want to predict a value y corresponds to the label of it. I just randomly searched for a linear regression figure here, which shows your grumpiness correlated with your sleep hours. But as we can see from this figure that just the predicted value doesn't tell us anything about your confidence or your uncertainty about the trend model. Like in reality, like how do we interpret this value? How it's close to the true value y. So to answer this question, some of people they trying to use the confidence set as a measure of the uncertainty, or like you use the confidence set to quantify the uncertainty of the trend model. As we show in the right-hand figure by Lei et al. There is a red thin line, which is a regression value, and also it has a pink band around it, which would be the confidence set. So it evaluates like how confident or uncertainty of the model. So this brings a very popular problem or a field called conformal prediction, which is as follows. We are given still a bunch of data points, x1, y1 to xn, yn. And we also given a coverage level alpha, which is between 0 and 1. Now we have a new new data with feature xn plus 1 with unknown label. And our goal is not just to predict one value, but to find a confidence set in the Y space such that the new data points label will fall in this confidence set with probability higher than 1 minus alpha, like reach the coverage level. Okay, this is a conformal prediction task we want to solve. And during the past years, there are already many conformal methods that are provided in the literature to achieve this coverage with very weak assumptions on the data. They do not even require the data is IID, they just only require data to be exchangeable, which means you can exchange the order of the data. For more details, I refer to Wolf et al. And Angela Paulus et al. Their books for more detailed discussion of these methods. However, there is a question that how good is the prediction set provided by this conformal prediction method? A natural way to evaluate how good is how large this or how small this prediction set is. Usually we want the prediction set to be small, which means you are more informative about your prediction. However, as we can see from this conformal prediction problem, the trivial solution, you just output the entire Y space. It naturally satisfies the coverage, even with alpha equal to 0, the best coverage you can get. And the most existing methods in the literature, they have no theoretical guarantees on the size of the prediction set they provided. And they usually evaluate their results by in an empirical way, like to evaluate its size, expected size or volume. Like the volume is the big measure of the prediction set.
Yeah. So what's the randomness in this probability? Like, is it just like for y conditioned on xn plus 1, or is
it also depends on the randomness of the history, the data samples x1, y1 to xn, yn. Yeah.
Wait, so you're not saying like for every xn plus 1 and every sequence you to do this, and you're just saying you are assuming there's a distribution of like x1, y1 to xn, yn.
Right. Yeah. Usually you need to with some assumptions on the it may not be ID, but you can consider you have a joint distribution of the whole sequence.
Okay, so then how do you actually evaluate this probability, the coverage of this 1 minus alpha in practice? Like, would you like to train the method like multiple times, sampling multiple data sets to evaluate if this?
Yeah, you can take multiple tries to.
Okay.
Yeah, the evaluation is a little bit.
Why is it called conformal? Conformal is something about angles, right?
It's because you're trying to like evaluate how similar to that point is, or like how close your prediction is to the true value.
Okay.
Yeah. In this sense. Okay. Yeah. Then this is really a challenge for the this problem. Like we actually want a small volume prediction set, but we only have methods to achieve the coverage. So here we proposed a goal of volume optimality. So we want to find a set that's both satisfying the coverage and also with the smallest volume. So yeah, this is a problem we want to solve. So in this talk, first I will formally define the volume optimality we defined, and then go to the one-dimensional setting. So the label space is one-dimensional. And first we talk about, in general, this is impossible to achieve. And then we propose a restricted volume optimality. And finally, we go to the high-dimensional label space. So first, let's formally define what is the volume optimality. We started from the most simple unsupervised setting. In this case, we can consider we have no feature x, or feature of x space is a singleton. Then we are given an arbitrary distribution D over the space Y. Usually we think it's a Euclidean space. And we have points that are sampled ID from this distribution. So we consider, for now, let's just consider a very strong ID setting. And now we want to construct a data-dependent prediction set based on Y1 to Yn, the historical data, such that the new data fallen in this prediction set with probability at least 1 minus alpha for some coverage level alpha we pick. Now the question is, we're trying to minimize the volume of this C hat, but the C hat is dependent on the history, so it's possibly it's a random variable. So for now, let's thinking about Y is some D is some continuous distribution on the single-dimensional space. So we can draw its density function, the probability density function here. And then in this case, the optimal solution for this question would be very easy. We just pick some level set of based on this density function, and this would be Z opt, right? So like we pick the most dense regions in this density. However, there are other distributions like discrete distributions or like other hybrid format. They may not have the density function, and in this case, we can still define the optimal solution, which is over all sets that achieves the 1 minus alpha coverage we want, and we take the infimum of the volume of those sets. So we can easily define the opt value. And now what we want here is so remember this volume C hat of our prediction volume is maybe random, depending on y1 to yn. So we want our volume is at most the opt of 1 minus alpha plus some slackness in the coverage epsilon in expectation or with high probability. So plus this slackness is because in reality, if you just pick the 1 minus alpha optimal solution, it may not even be a measurable set. So although comparing to the opt 1 minus alpha would be a valid question, but it might be very hard.
Just going back to Julian's question. So here, though, this probability now is only over yn plus 1.
No, here the with high probability is also over the entire
the definition of opt.
Yeah.
When you define opt,
opt is.
when you define opt,
opt is only depends on the distribution D. So
it's only over looking only at the last point.
The opt only the opt does not depend on any data point, right?
Right.
It's just captured by the distribution, and but your volume, your prediction set and the volume will depend on the entire history and the yes.
So when design this data dependent set C hat, does it allow to be a function of D? Do you want same mapping from y1 to yn to C hat, which works for every D, but it's not known to the algorithm?
Yeah. Your method does not have any information about D, so you want your algorithm to work for any distribution.
Right. So you have to be, the key point is epsilon volume automatically for some epsilon, and you have to work for every D.
Yeah. This is work for every D.
Okay. Otherwise, it's trivial.
Yes. Before we go to our result, I want to say there are other definition of volume automaticity in the literature. The one is you capture the volume of your prediction set and the difference of the volume in your prediction set and the optimal prediction set, C opt here. However, this requires the optimal prediction set to be unique. Otherwise, this difference can be very large. So usually for those type of work, they require additional assumptions on the distribution D, you want the distribution to be not constant, and you want the distribution to be smooth. They add additional assumptions on the distribution. But in this work, our optimality does not require such additional assumptions on distribution. So it's truly distribution free. Okay, first we will talk about the one-dimensional space and saying about the impossibility result. So in general, it is impossible for any distribution-free method to find a non-trivial set, achieve the coverage, even when there exists one non-trivial, pretty small confidence set. Specifically, it's for any epsilon. If you give me some method you claim it's distribution free, we can find a distribution D such that in expectation your volume of prediction set is at least opt 1 minus alpha plus epsilon. So consider epsilon very close to alpha, then basically your volume should cover everything. So it's a trivial solution. You only can output the entire space for this specific distribution.
I'm curious, where does the quantifier over the number of observations come in? Can you show methods? Can you get a single distribution? So if the amount of data goes to infinity?
Oh, that's not. It's you fix a number of samples, then I can create a distribution depend on the number of samples. Okay. Yeah.
But can you be consistent? Or maybe you're going to show that later. Is it possible to have methods that are asymptotically consistent then?
If you have a very large amount of the samples, then I think it's possible to get some volume of that. Yeah. So the way you show this is so to answer your question, you really need the number of samples to go to infinity. Like asymptotically, you can achieve this kind of optimality. So the intuition of how we prove this is from the hypothesis testing. So you can consider the two cases. The yes case is you are considering the true distribution is a uniform distribution supported on everyone. And the no distribution is you take a mixture of distributions supported on n samples from this uniform distribution. Then these two different distributions will be very close, where in terms of the prediction set for the no case, you can actually just have output a prediction set supported on those points. So you get a really small volume prediction set. While in the first case, you need to output long intervals to cover the probability mass. So the issue for this kind of impossibility result is that if you consider you fix some large n, then this no case is really supported on those endpoints, and your prediction set would be only cover those n isolated points. So the general prediction set can be very complicated, and in this case, it's very hard to output a very nice confidence set to predict to cover the probability mass. Okay, yeah.
I maybe got confused with something. So if I just look at collision of points, in the no case I'll expect to get collision. So if I know that I have to distinguish only between these two cases.
Oh yeah, that's a very good question. So this is basically an intuition. So there are two ways to solve this. One way is you can slightly extend your mixture distributions, not just spotted on these endpoints, but slightly increase it. So you have a tiny bit of interval to reduce the collision. Or you can just sample much larger than your sample size, like n times a large factor, such that you will have very low probability of collision, and you still can bound the distance. Okay. Yeah, so this is just a technical thing. Okay, now we want to, so given this kind of strong impossibility result, what we can do is we try to achieve some restricted volume optimality. So restricted in what sense is, so remember before we talked about the issue is the general prediction set is too complicated. So can we restrict ourselves to like nice and interpretable prediction set? So we consider the set family Fk, which is the union of k intervals. So if you consider single dimensional space, interval is the most nice thing you can think about to cover the probability mass. So k intervals is also still quite interpretable and less complex. And the good thing is for fixed k, it has a finite VC dimension, depends on k. And now our goal is to get the epsilon volume optimality with respect to this prediction set, prediction set family.
So the volume is just like Lebesgue measure?
Yeah, Lebesgue measure.
Does it have to be Lebesgue measure, or it can be everything? It can be any measure?
Yes, yes, I think it can be any measure.
So does it make more sense to like think about special case where your volume C is actually just PTC?
Oh, just the probability.
Yeah. I mean, it's just like a natural measure you would care about, right?
But in that case, since you are already heading to get the coverage over the probability measure of D, then you get 1 minus alpha, right?
Right. But then the requirement becomes like find the C hat such that the PTC hat is smaller than like 1 minus alpha plus epsilon. It's kind of like something like an intrinsic notion with volume.
I mean, that you're getting more into, that's really a calibration issue then. Then what you're asking for essentially is calibration.
But in one dimension, it's like that, like all the statistics. Okay.
No. Okay, we'll talk about that later.
Yeah, we can talk about it. I think that it's not easy to like stretch your distribution such that the measure is like the probability measure. Yeah.
You could also be outputting answers which are not in the support of the distribution. Answering intervals, they might not be in the support.
Not in the support, then you just waste some measure, I think.
Well, not based on Juan's notion. With Juan's motion, you get that for free. No, I really think you'd. I mean, let's talk about that. Your motion just amounts to having a calibrated.
Yeah. Okay. Then, our current goal is to get some optimality with respect to this restricted family. And the first result we show is that we propose a new conformal method called conformalized DP based on dynamic programming that achieves the coverage always, and also it achieves epsilon volume optimality within this set family with high probability. So how we do this is we can first forget about the distribution setting and focus on the empirical version of the task. So empirical version is you're just given n data points, y1 to yn, and we try to find the smallest volume set in the family that covers 1 minus alpha times n of those points. And this task, we can easily solve it with dynamic programming because it is on a single dimensional space. So we can enumerate the last interval and the endpoint before that. And now we know how to solve the empirical version. How do we go back to the distributional version? Is we can see that as the number of samples increase, the empirical distribution Pn will actually getting very close to the true distribution P, since the BC dimension of the family set Fk is bounded by K. So very close is in terms of the set inside of the family. So the distance between these two will be very close. However, if we directly use this to go back to the distributional setting, we will require that the number of samples n to be large enough, like at least much larger than n, we can get the coverage. But the conformal prediction.
I'm a bit confused. Isn't n the number of samples?
Yeah, n is the number of
What
samples.
do you mean the number of samples is much larger than n?
So you want this like gap between the empirical distribution and the true distribution like to be very small. So here the bound is square root of k over n. So you need this thing to be much less than 1. So you want n to be large.
But larger than k.
Yeah, larger than k. Then
Okay, fine.
Yeah.
But, okay, sorry. I thought you said larger than n. Okay.
Oh, okay. Yeah, larger than k. But you want the coverage here to work like no matter how many samples you get, even small number of samples, you still want the coverage. That's the conformal prediction wants, because it's saying if your prediction is very nice, then you get the coverage and both the volume of optimality. But if your prediction is bad, you can at least get some kind of coverage.
I'm a bit confused, but if n is small, like if n is 1,
Yeah.
I mean, it's not much better I can do than just return
Yeah,
the
you
entire
just
interval, right?
output the entire space.
So
Yeah.
what's wrong with that?
So
Like, why can't they just, if n is small, I'll output the entire thing?
yeah, that's what we eventually we do.
Oh,
We
okay.
like put the conformal wrapper on it. But if you're just using the DP solution,
Okay.
yeah, you will not get like even the DP solution tell you I cover this particular data point, it will not give you the coverage. So the idea is we take the DP solution and we put it in a conformalized wrapper. So how we do it is, so for now we consider a split conformal setting for a framework. We have, for now we consider 2n historical data, and we split it into half and half. and we use first half to run the DP to get the to predict a set of intervals that achieve the coverage on the first half and with the smallest volume. And then we construct a nested system, like we greedily shrink these intervals and extend these intervals to get different levels of coverage from 1 over m to entire coverage 1. So Sj would be in the middle level, which is our DP solution. And then we can compute the conformity score on the second half as a validation process. So we use the second half data to validate. How we do that? We compute the number of stats that covers a particular point y in the second half. And if covered by many intervals, then this y is in a lower level of the probability mass. And if covered by small one, then it's very high. Covered by a lot of stats, then it's very high. And covered by a small number of intervals, then it's very low. And then we can output the prediction set based on this score. So we set a threshold at the n plus 1 times alpha divided by n quantile of this score. So this is a standard conformal method to output the prediction set. Yeah, so an analysis of this method to achieve the theorem is based on the standard conformal analysis. It's just a conformalized DP solution. So yeah, this is a story for the unsupervised setting in the single-dimensional space. And here we compare with some previous method called conformalized kernel density estimation. So the kernel density estimation is we try to directly estimate the density function and then pick the level set. So as we go back to the beginning, if we have the density function, then we can pick the level set. We get some coverage stat. The conformalized kernel density estimation KDE here has a problem issue is the parameter, the bandwidth parameter. How do we pick the bandwidth? So as we show here, if the bandwidth is too small, then the kernel density estimation might overfit the data. As we can see in the most left figure, it creates very tiny intervals and trying to cover the empirical data. This is probably not what we want. And when the row is too large, it may underfit, such that for some tiny Gaussian data, it creates very large band. However, in our case, at least when our choice of the number of intervals k is larger than the required mode, the actual mode in the model, then we get the good solution. So here we show k equal to 3, but actually if you pick k 4, 5, 6, it still keeps the same. So it's pretty stable in terms of the choice of parameters. And we also get very good volume comparing to the density estimation thing.
Why do you choose m?
Sorry,
Why do you choose m, the number of the nested set?
Oh, the nested set. M is something you will finally eventually get in the selectness of your coverage. So usually you could consider take m is 100, then you get 0.01 in the coverage thing. So it's probably pretty good.
Wait, I'm a bit confused. So you can choose. How does this is your epsilon, right? The 0 point.
Yeah, epsilon.
So, but presumably there's a limit to how. I mean, that the best epsilon you can get relates to
Oh, but in our case, it's like this epsilon is as small as possible, but the thing is, your algorithm will run pretty slow. It's just you will have 1 over epsilon times slower in the running time. But in
How can it be just a runtime issue, right? If I have a small number of samples, I shouldn't be able to get small epsilon, no matter how long I run. Or do you consider
right?
consider running as I can collect more data also?
No. You are right. The n cannot be much larger than n. Cannot be larger than n. So it's at most n. But here, because we usually run our experiments with number of samples is greater than 100, so you can consider. So you will lose a 1 over n in the epsilon in the slackness.
Which is the best I can get.
Yeah.
If I don't care about runtime, the best is to choose n equals n.
Yeah.
Okay. And then I get epsilon is 1 over n.
Right. 1 over n is necessary.
Okay.
But here is like for row, if you pick very small row, you get bad, and pick very large row is bad. So it's not very intuitive how to pick the best bandwidth for general distribution. Okay, next we will go to the supervised setting, where you not only have the label y, you also have the feature x. Now the goal, except the marginal coverage and the volume of mapping, you also care about the conditional coverage, which is conditional on a particular feature xn plus 1. You still want the coverage to hold.
Question. So in terms of marginal coverage, so if I give you 2 test data, and you make 2 conformal prediction on the 2 test data, can you say some joint probability of this coverage on these 2 test data?
2 test data.
Does that like this kind of like a
No, I think in terms of marginal,
like what's the
you
probability
mean
of this?
conditional on these 2
No.
specific axons?
No, just the conditional all the randomness. What's the probability that both 2 test data are covered the steps?
Would that just directly go back to the marginal coverage thing? Because it takes the randomness over xn plus 1, right?
Well, it's at most 1 minus alpha, 1 minus 2 alpha, right? But it could be, I mean, just by union bound, right? It's at most 1 minus 2 alpha.
Yeah.
But you're asking if can you guarantee that it's less than that? It's more than that.
Yeah.
Like,
In particular, would it be
Yeah.
1 minus
I
alpha
think
squared?
it's 1 minus
1 minus 2 alpha
Two
would be always because
Yeah, but does it like a
or 1 minus 2 alpha plus 2 epsilon.
But I think you should get 1 minus alpha because you are taking the expectation over this random data point choice, right?
Maybe we should talk about that later.
Yeah. Okay, but the conditional coverage thing is something very hard to achieve in general because if you have no assumptions on distribution or your learning process, it's quite possible that you have a very new data point, xn plus 1, and you have nothing about this conditional distribution on this xn plus 1. And it's very hard to achieve any conditional coverage. This is already shown by Wolfgang et al. And in our case, we combine our previous conformalized DP with a distributional conformal prediction method by Chernow-Zukov et al. So their DP framework relies on the quite accurate estimation of the conditional CDF, which will be the CDF distribution conditioned on some particular feature X. And here, we also require this kind of assumption to have a conditional CDF estimation, which is accurate enough. Then, based on this kind of assumption, our method can achieve both marginal coverage and conditional coverage with high probability, and also epsilon volume automatically with respect to the family set K intervals. So how we do this is we still split the data set into half-half, and we use first half to estimate the conditional CDF. And now you have for each x, you have the for each feature of x, you have its conditional CDF as distribution. And now you can generate as much number of samples as you want from this distribution, and run. Now based on these samples, you can run the DP on it and construct the nested set as before. The good thing is after you construct this nested set, it will bring for different x feature values, like the conformal score is between 0 to 1. So basically you scale this kind of uncertainty in the same level for different feature x. And now you can use the conform method to output the prediction set. So you can consider of this nested system as the discretization of the quantile space. And based on this quantile space discretization, you can you can map the points in the validation set to the conformity score. Yeah, but the guarantee requires that the conditional CDF is accurate, but in general, it's very hard to do. But we claim is to estimate the conditional CDF is at least easier than estimating the density function itself, the conditional density itself.
So I'm a bit confused. What is this conditional CDF? This is CDF of what?
The conditional CDF is you want to have an estimation of given some feature x, the cumulative density, cumulative distribution function of y conditional x.
But
so if you can consider,
I'm a bit confused. If you had that, wouldn't you be completely done?
If
I mean, if you really trusted if you have the correct one, if you have the true
if
one.
you have the true CDF, then you are done.
But here you're assuming that you have the true CDF.
Now we assume is we have a noisy estimation of CDF. So this is slightly easier than getting the good estimation on the probability density function itself, because the density is unbounded, but the CDF is monotone and between 0 and 1. So get a noisy estimation for conditional CDF, we think is weaker version of getting directly estimates the density function.
I mean, okay, maybe when you describe your guarantee, then I'm just curious, how does this translate to an actual conformal prediction guarantee? Because I get some CDF, I don't know how good it is.
So yeah, I didn't write this assumption clearly, but actually what we want is for any set C in the set family, which is the union of K intervals, we want our prediction of the conditional CDF and the true CDF on this set is epsilon close, delta close.
But you're taking that as a requirement, as an assumption.
Yeah, we take that as an
I see,
assumption.
but that I have, okay.
Yeah, this thing maybe strong, but our claim is it is at least easier than directly estimates the density function.
So instead of maybe an L infinity approximation of the probability density function, you're doing some Kolmogorov distance?
In our case, it's easier because this CDF is bounded between 0 and 1. So also we are averaging over intervals. So it's much easier than directly estimate the density, because density you can have discrete distribution, then it's very hard to estimate the density itself. Yeah. Also, there is one direction we are trying to explore now is here. We see that in our algorithm, we actually does not require CDF explicitly, the conditional CDF. We only need to generate some samples from the conditional CDF. And this is something this kind of generative model are good at. Like you have a bunch of data and you have new X and you want to generate a bunch of samples that looks quite similar to the previous data. So what we are trying to do is we try to use some DAE or diffusion models to generate these kind of samples. Yeah, but that's the open direction. Oh, okay. Yeah, and this is the experiments comparing to the current best thing, and we can see here our prediction method can output like disjoint few intervals that has much smaller volume comparing to the previous conformal method, which only outputs one interval for each x. So because here we have more freedom in choosing prediction sets. Okay, finally I will like slightly go to the high-dimensional setting and talk about our results. So now we consider we are in the high-dimensional Euclidean space. A naive approach to run the conformal method is to run the single-dimensional method on each coordinate separately and then combine each coordinate's prediction set. And this will give us a rectangular space, a box here, a blue box. However, what if the true dense region is something like this red ellipsoid? Then this prediction set is very bad in terms of volume. And in practice, by Blay et al., Blay and his students, they already trying to output the union of balls to cover the dense regions. And now our question is, can we find a ball or union of balls that's compatible with the best ball or union of balls to cover probability mass in high-dimensional space? And why we pick ball? One reason is ball is the most natural thing in the high-dimensional space, and also the VC dimensional ball is bounded by d+1. So you will have the generalization bound for the balls. So again, based on our previous observation, we can focus on the empirical version of the task first. So we have n data points, and we just trying to find the smallest ball. So first we consider one ball, and we want to cover delta fraction of that. Luckily, a previous work by Badu et al., they already can find a ball with radius approximation 1 plus order 1 over log d. So in terms of volume, this gives exponential in d over log d volume approximation. So this is pretty good because a naive boundary will get 2 to the d in the volume of approximation because it's easy to get a 2 approximation in radius. However, in this work, we first show that it is NP hard to find a ball with that covers delta n points with volume approximation better than e to the d power 1 minus epsilon. So epsilon is any constant. So get d to the 0.99 is NP hard. And the observation is that the hard instance, the points in this ball, actually lies in a low-dimensional subspace. So yeah, these points are in a low-dimensional space. Then a natural question is what we can do if the instance is not the worst case, like in this low-dimensional space. So we show that if the points in the ball, in the optimal ball, is actually isotropic, then we can get some better bounds in the volume approximation. So the isotropic here means if the optimal ball covers delta n points y star, and y star in the ball has covariance matrix. All eigenvalues is bounded by beta times r star, the radius squared divided by d. When this beta is very close to a constant, then it's more isotropic. If beta is D, then it's not isotropic in some sense. And when the beta is a constant, it's the most isotropic case, then we get e to the square root of D approximation in the volume. So we get much better than the worst case. Because the worst case is e to the D over log D, and the harmless is e to the D to the 0.99. So what we get is actually a root D if we know that the optimal ball is isotropic. The points in the optimal ball is isotropic. Okay, how we get this non-worst case bound is the observation is that now consider this ball is the optimal ball and the red points are the points containing this ball. And if we know the covariance matrix has bounded variance sigma, then if the mean of y star is very far from the ball center, then actually most of the points are closer to the mean than to the center. So we can pick a ball like shifted towards this mean mu star such that it covers most number of points inside the ball and still with a small radius. So this is the first observation here. The many points in the y star actually closer to mu star, the true mean of y star. And second thing is with least decodable mean estimation, we can find mean estimation mu hat very close to mu star. And combine this, we can find a good ball that cover the points in this optimal ball. And finally, is what if we are not considering ball? Can we find some other smaller prediction set that comparative to the best ball? In reality, like we usually feel the long baguette is like in terms of volume is much smaller than a round sourdough. So a natural question we are thinking is whether we can pick a small ellipsoid to cover the dense regions. And the small ellipsoid has also a small VC dimension and interpretable. And also we can stretching it towards some high variance directions to cover points better. As we show in this figure here, we can pick an ellipsoid to cover these red points. And we show that in the worst case, we can even pick an ellipsoid that contains a large fraction of points, such that the volume is e to the d to the 2/3. So still much better than the worst case for the proper learning with the ball. So this is in like general case. Yeah, sure. And the intuition for this is still like using our previous observation for non-worst case proper learning. We can find the large eigenvalues of the covariance matrix of y star, and there are not too many of these kind of large eigenvalues, and we can run a transformation to shrink these large variance directions and to go back to the isotropic case. And this when we find a ball in the transformed space and go back, we get ellipsoid in the original space, but still with a small volume guarantees. And due to the time limit, I will briefly talk about we can also get a greedy algorithm to get pretty good approximation for union of balls in terms of both proper learning. We find the union of balls, or we can find a union of k ellipsoid to comparative with the best union of k balls. And there are a few open problems. The first is, as we discussed before, in the supervised one-dimensional setting, our conformalized DP only require generate samples from the conditional CDF, and it does not require the conditional CDF explicitly. And can we use some generative models to do this step? The second thing is, can we prove some lower bound for improper learning with ellipsoid? We conjecture the lower bound would be e to the square root of d, and also like whether if this is true, whether we can improve our upper bound. And the improper learning we explore with other norms. And finally, here we use the volume, like Lebesgue measure as the measure of uncertainty of prediction set. Can we use different kind of measures? Yeah, maybe as Zhiyan said, we can use some other distribution measures or some measures given by downstream tasks. That's all.
Questions? So, actually, I have the same. Wait, there is a question there? Oh, okay. I have the same question I guess than before. I'm still a bit confused because it seems you're requiring as a starting point to have a method that returns a somewhat accurate CDF. Can I mean, how can I? But if I don't know that that's satisfied, then I don't have any of these controls.
Oh no. Even your like conditional CDF is completely wrong. You still, if you use the conformalized method, you always get the marginal coverage.
Oh, okay. So you always agree.
Yeah, you always get the
even without
this assumption.
Okay.
But to get the conditional coverage, people already shows that without any assumption, you cannot achieve this kind of conditional coverage, and also the volume multiplicative, you cannot achieve this kind of thing.
Other questions? Yeah. So one reason I propose to use the underlying distribution D as a measure is because, say you have different ways to like describe the objective, like pre-training loss versus like perplexity, which is like law exponential of the other. But if you do conformal prediction for loss, and then you cannot transfer it to like perplexity, because just take exponential, the volume changes.
How does the loss come in? There's no loss here.
No, I'm talking about, say, you want to do conformal prediction for the training loss of some language model, right? Okay. And you can also talk about this loss by like perplexity, which is exponential loss, right? And you want, even if you have good, very conformal prediction, very for small volume set for the loss, but you don't have that does not really give you a good small volume prediction for the exponential of the loss, even if it's the same objective.
Small volume just under a different measure.
Yes. I'd like to have something like invariant on this, like all these transformations, and then natural candidate is to use the underlying distribution D, which is invariant to this. But I think it's natural to.
Yeah, but then, you need some kind of stretch the transformation of your like prediction such that the high density region is actually.
I think that's actually all it is exactly calibration, because all the property you get is that you get something that it really actually has probability alpha. That's the only thing that you're basically getting, which is exactly calibration. You're not necessarily saying that it has a small that it's small in any way, right? Because in particular, it can be way outside of the support. I think somebody mentioned, right? I mean, you're not. So I think that's a very different type of objective.
Okay. Yeah, I think it's highly related to the calibration is not design.
Okay, so maybe I don't understand why like the difference between conformal prediction and calibration is an issue.
Well, I think there is a connection. Like when the label space is finite, then I think by Aaron Ross et al. They proved that the calibration is easy and they can do for the conformal prediction, and the method over here is quite similar to when Y is like discrete, finite discrete space. They basically is also running a DP type analysis. And probably in the like real space it has like other kind of relations. You need to see offline.
Yeah, but maybe we will take this offline. Okay, so thank you very much.